Last episode, we trained a frontier model across 1,000 GPUs, 3D parallelism, sharded optimizer, and CCL gluing it together. Now we have a trained model, and a trained model is just a file. Production is everything around that file that keeps it answering, fast for thousands of users with nobody watching it at 3 in the morning. Let's build that. First, the model needs a home. These GPUs live in specific machines. A DGX Arch 100 is 8 Arch 100s wired together with NVIDIA switch and 900 gigabytes a second of NVLink plus 8 network cards for talking to other boxes. Stack many DGX nodes behind an InfiniBand spine and you get a superpod, an AI factory. And the newest tier, the GB200 NVL72, fuses 72 Blackwell GPUs into one NVLink domain that behaves like a single giant GPU. Second, you wrap the model in a container. The reason is brutal. GPU code is fragile about driver and CUDA versions. NVIDIA's NGC containers ship the whole stack, CUDA, CUDNN, and CCL, pre-tuned and matched. You run them with the NVIDIA Container Toolkit and a single flag GPUs all, and it runs the same on your laptop and in the cluster. Third, you hand those containers to Kubernetes. The foreman that places them restarts crashed once and scales up under load. But Kubernetes doesn't know what a GPU is. The GPU operator teaches it. It installs the driver, advertises each GPU as a schedulable resource, and can even slice one H100 into up to 7 isolated instances with MIG. Then, kserve or the name operator turn your model into an auto-scaling service. It can even scale to 0 when nobody's asking. Fourth, and most important, you watch it. A service you can't see is a service that dies quietly. NVIDIA's DCGM exports GPU telemetry into Prometheus, and Grafana draws the dashboard, GPU utilization, and crucially tensor core activity, which is the real "are we using the silicon" number. On top of that, your serving engine reports the 4 KPIs that matter: time to first token, inter-token latency, throughput, and KV cache utilization. Add drift detection and latency SLOs, and you have an on-call dashboard. And when the dashboard goes red, the rule is roll back first, debug later, flip back to the last good image, get the service healthy, then find the bug offline. Build it to bend, not snap, per request timeouts, a circuit breaker that sheds load, and a fallback answer so a partial failure never becomes a total outage. Let me draw the whole production stack as one picture, from the metal at the bottom to the dashboard at the top, because this is the system NV48 is going to stand up for real. We'll build it bottom up. The foundation, a DGX class node, 8 GPUs on an NVIDIA switch fabric, and a superpod spine of many nodes over InfiniBand. This is the where. NVLink inside the box, InfiniBand between boxes, exactly the rule from last episode. On top, the container layer, an NGC image, NVIDIA green, wrapping the serving engine, TensorRT-LLM or vLLM, with the model weights, run it with the container toolkit. This is the unit Kubernetes schedules. Now the Kubernetes layer. The GPU operators green runs on every node, driver, the device plugin advertising GPUs, the DCGM exporter, the MIG manager slicing one GPU into isolated instances. Above it, kserve and the NIM operator place the inference pods and autoscale them, and the observability spine lights up on the right. DCGM and the engine metrics flow into Prometheus, then Grafana, TTFT, inter-token latency, throughput, GPU, and KV cache utilization drift. And the bracket around everything, NVIDIA AI Enterprise, the supported secured SLA-backed version of this whole stack, shipped with Blueprint's U-fork, instead of building from scratch like the RAG reference architecture. So now we have the substrate, GPUs, containers, Kubernetes, a dashboard, and an enterprise wrapper. There is only one thing left to do in this whole course: stand up the entire production assistant on this end-to-end. That's the capstone. Thanks for watching. Thanks for watching. Like and subscribe for more videos like this, and I'll see you in the next one.